A very good morning to our lecturer. We are Group 3 from Section 2. My team members and I are doing a case study about the failure of continuous beam in school. Let us present the issue in this video. The structural test that we conduct in our investigation is cracking test. There are several methods available depending on the testing task. There are visual inspection, line penetrate testing, eddy current testing, tomographic testing, magnetic particle testing, and ultrasonic testing. The more common crack testing is with visual inspection. During visual inspection procedure, the surface-related quality features like shape deviations, defects, or the surface condition of a component are observed and assessed with the naked eye or with the aid of optical devices, such as magnifying glasses, microscopes, or endoscope. The another test is with eddy current instrument. Eddy current technique has become the standard approach for survey inspection of conductive workpieces. A test instrument is a related probe, and if required, the additional software module make up eddy current test system. Then, the magnetic particle testing is the earliest technique for identifying material defects. This technique involves magnetizing and misting magnetic powder onto ferromagnetic components. Different test part flow respond to the magnetization in different ways. The magnetic field is now more prominently seen on the surface. The magnetic powder can have a fluorescent material added to it to make the flow glow in different ways depending on the illumination.
Next, we will talk about the beam analysis. In this project, we consider about 3 cases as stated in the presentation slide, and I will take the case 1 as an example to explain how we're going to carry out this. The first step is we have to draw the free body diagram by using the information that we have, and we will use the formula 1.35 GPa plus 1.5 QK in order to get 49.68 kN per meter as the load acting on the entire beam is the maximum load. Next, we will calculate for the member stiffness. For example, for the KAB is equal to the 3I over L. This is because it is supported by the end support. And then we will sum up the member stiffness according to their joint in order to find the joint stiffness. And then we can divide the member stiffness with the joint stiffness to get the distribution factor. Next, we are going to find the carryover factor for each member. For example, the COAB is equal to the COBC, which is equal to 0.5. Next, we will calculate for the FEN, which is the fixed end moment, and we will get the answer equals to the 232.88 kilonewton meter. Next, we will put all the answer into a table in order to help us calculate it by using the moment distribution method. And we have to balance all the FEN over here. For example, at the A, we will get the FEN equals to negative 232.88. Then we have to balance it with the positive 232.88. Then the carryover factor for the AB is equal to 0.5. Hence, we will carry half of the FEN balance at here into the BA. Then we will continue the procedure until we get the moment at here less than 0.5. Next, after we get all the landing moment, we have to find the shear force. For example, we can take the moment at the B equals to 0, then we equals the clockwise moment to the counterclockwise moment. Then we are going to find the shear force AB. And same things goes to the shear force BA. Then we will do the same thing for the span BC and the span CD. Next, we can use all the calculated answer in order to help us to plot the diagram for bending moment and also the shear force diagram according to the positive direction.
Furthermore, based on the shear force diagram, we can determine the support reaction for each point. For case 1, the highest support reaction is at point C with 409.64 kN, while for case 2 is also at point C but with 299.99 kN. Lastly is case 3, with 431.08 kilonewton at point B. So obviously, we can see that the highest support reaction exists at case 3, point B, with 431.08 kilonewton. So this point should be used for design process, but somehow designer will misdetermine the highest shear force as case 1 has the most applied load. But in this case, we know that case 3 has the most highest shear force. Hence, it might be unsafe or it might be or the bucking might be happen if misdetermination happen. Next, we should base on the three cases and determine the highest negative moment and highest positive moment for us to carry out the design job. As you can see, the highest negative moment is at case 3 at point B with 305.89 kilonewton meters, while for the highest positive moment is at case 2, which is at span AB and CD, which with 256.30 kilonewton meter. And we know that the highest negative moment is the maximum hogging moment, while the highest positive moment is the maximum sagging moment. So both of these values should be taken into account in the design process later on.
Region of failure. So the region of the failure of the beam can be the inadequate of the area of steel provided due to the mistake in the calculation of the highest bending moment. So the calculation of area of steel required is based on the highest bending moment. If there's any error or mistake, the failure or cracking will happen. So let's look at the formula. This formula is used to calculate for further use to determine the maximum spacing and also the maximum size of the steel bar. So the value of GK and QK in this formula is unchangeable due to it's the calculation based on the design. The only value that we can make decision is the area of steel provided. The value of area of steel provided should be at least 50 millimeters square more than the S required. Here's why. For example, we have the S required calculate is 105 millimeters square. So we just decide that put the S provided with 110 millimeters square. However, the S required we calculated have some error, which in fact the S required should be 120 millimeters square. So if we just put the S provided 50 millimeters square higher than the S required, in this case we can avoid the cracking of the beam.
How can we retrofit the continuous beam to make sure it can safely transfer the forces to the columns? The method of beam retrofitting is by concrete jacketing. This involves placing an additional layer of concrete around the existing beam and placing the additional longitudinous bar in the beam, so it can enhance the shear capacity and fractional strength of the beam. So next, the concrete jacketing can improve axial and fractional strength in the beam. Also, the load-bearing capacity of the beam will increase. Therefore, the structure is capable of carrying axial and bending moments. After the jacketing, the columns are able to carry the working loads that works significantly in column capacity, especially when there is an increase in moment capacity. In addition, the additional longitudinous bar of the beams should be secured to the column's reinforcement for the transfer of moment between the beams and column in a rigid joint. In conclusion, we have to determine the applied load for three cases and the most critical force as well as bending moment in order to ensure that the reinforcement is able to withstand the applied load Hence, the building will be safe from the collapsing. Moreover, by proving some retrofit methods, we are able to add more allowance for withstand load of column and beam. Not only that, by proving a higher stage of reinforcement will also help in avoiding in this such failure. So that's all for our group. Thank you.